Okay, so let's go over this starters 153. Butterfly. Okay. Yeah, so this one, butterfly, you're given the number of red butterflies, green butterflies, and blue butterflies, and you're also given number of flowers in terms of each color. Um, and you're only given R, G, and B once. And so the number of butterflies is equivalent to the number of flowers. Let's see. Okay, so for this one, if you have like 2, 5, 4, it doesn't really matter. But if you do like one example, like let's say there's one example that is red, blue, green. So what can you do for the red butterfly? And you have the blue, and then you have the green. So for the red one, you can give them green. I don't know, like that. For the blue butterfly, it can be red, red, green, green. Okay, but then you're out because you already used 4 greens, you already used 2 reds. So obviously, you have to use another green here, which means that over here in this red, you should have used a blue, and then you can use the remaining 4 blue for here. So all you had to do for this one is kind of realize that if you sort this 2, 4, 5, it basically is going to work as long as this prefix sum, or the sum of these two, the two smaller elements, as long as that sum is greater than or equal to the largest value, it will work. And I guess the reason why is just, I don't have like an exact proof, but like if this is 5 or greater, that means I can distribute all of this and all of the red and green into this one. So like if this was 1 and or no, let's say this was 2 and 3 and 5, then I could distribute all of this here and distribute all of that here. And then this 5 is enough to distribute into both of these. And if this was even greater, like 2 and 6, and this is 10, well, this isn't actually going to work because I only have 8 to distribute into here. But if it was like 6 and 6 and 10, now I have like 12 I can distribute into here, so it's good. And then whatever remainder I have, I can distribute this 10 into these two, and then whatever remainder I can distribute into them individually. So it's yeah, it's not as easy as it looks. Actually, kind of tricky to figure that out. But I mean that's it. It's just using the sum of those two and the sum of that one. It's kind of hard to like believe it because like, well, okay, well, could this ever be the case? Like, what if you have 6, 7, and 8, right? It's like, okay, now you can distribute all of these into here, right? Well, you don't have to distribute all of them, but it makes the most sense to maybe distribute the 7 into here. So distribute the 7 into the 8, and then distribute 1 from here. So then you have 5, 0 remaining flowers, and you would have already, and you have 8 of these remaining, and you've already satisfied this one. So then you want to satisfy this one here. So you're going to use this one first, and then use this, but you need 7 total, so you get 0 here, and 0 here, and then so 5 plus 2, so that you have 6. So then you'll have satisfied this one, and then you can use the remaining 6 into here. I don't know, like if you just simulate an example like that, I guess that's kind of informal proof as well. So the code is really Oh, I think I left in something that I wasn't using before. Okay, yeah, these I'm not using right now. It was my first solution. Um, yeah, so this you just need that prefix sum of this too. I mean, you could also, and then you do want to do the sorting. Um, yeah, and just check that it's greater than equal. Okay. This one another game. Even a integer. You have a permutation, and the goal is to sort the permutation in ascending order. But to achieve this, Bob can only perform these operations. Choose two indices such that the sum of them, the two values, is less than or equal to k, and swap pi and pj. So, once you find the minimum value for k, so the minimum value you can do to swap elements and get it sorted. Um, and so if it's already sorted, it's 0. This one is 5, and this one is 3. Um, but the trick to this one, the observation, really is that if you have like 5, 4, 3, 2, 1, this is obviously not sorted, but I'm going to say k is 6. And the reason k is 6 is because 5 and you're never going to never swap 5 with a number like these. Always swap 5 with 1. Essentially, what you can do is you can use the 1 to swap every other element. So let's say you have, this, right? So these are already sorted, but these are not in correct sort. So that means you're going to have to do some type of swap. And I argue that you can always swap through 1 to make this sorted. And given that the answer will always be the maximum value of an element that is not in the correct location, um, plus 1. So, and the swaps can work like this. So this one you could get into proper location because you can just swap. I mean, you can just swap the here. You can do put the 6 here. And now you can say, well, get the element that should be here with the 1, right? Well, you can do that. And now get the element here that should be here. You can do that. And now you can swap with the 6 again, and you have it sorted just by swapping with the 1. So that's the trick there, is just knowing that you can swap with the smallest element. So really, you just have to find the largest element that is not equal to its index. So I just take the max if it's not in the, if the element is not at its index, which is 1 index, so I add 1, and then you just add 1 to the max. Okay, colorful tree, easy version. Yeah, so the hard version is, so the easy version, the only difference between the two versions, the hard version asks you to count the number of colorings of the tree. But essentially, this problem asks you to color the tree with 3 colors, red, blue, or green. So it's 3 coloring of the tree. But you want to do it in a way such that um, you minimize the sum of this score, where this score is basically the calculation of the minimum distance to the other 2 colors. So if a vertex is green, it's the minimum distance to a node that's colored blue and a node that's colored red. And it's minimum distance, so it's the nearest blue and the nearest red vertex to that green vertex. I'll draw it out a bit more. And you just want to minimize this value. And the hard version just asks you to count, which is a lot more tricky. This one ends up being very simple. You don't need those actually. Um, okay. I don't know how to say very simple, but just like if you just mess around with a bit, you can find a pattern. So the very simple thing is that if you're going to have at least 3 nodes, and the very simple coloring is you can pick any color here, but choose a different color. Make sure you pick 3 distinct colors like this. And if you look at this, what's the total score of this one? There's 1 distance to the blue. So the distance to blue plus it's going to be distance to green. That will be the value for this node 1, the score for node 1. The score for node 2 will be the distance to red plus the distance to green, and the score for node 3 will be the distance, the shortest distance to red and the shortest distance to blue. And as you can see, the distance to blue is 1 here, and the distance to green is 2, so that's 3. Here, the distance to red and distance to green are both 1, so that's 2. And here, the distance to red is 2, and the distance to blue is 1. So that's 3. And so if you kind of draw a backbone of this thing, or you draw like a graph, a tree, and so my argument is this: if you take this red, then you're going to color this blue, and then you're going to color this one green. And well, okay, let's not do that. Let's just say down this line, you're going to keep just going red, blue, green, red, blue, green. And then you're going to color, what would you color this one? Well, it has a blue here, a red here. So it actually doesn't matter, but we'll just do green. Like green and blue will go to blue, and green and blue will go to red. So it doesn't really matter. And the color for the one here, again, it doesn't really matter, but you just don't want to do, well, yeah, you could do green. You could do green. No, you don't want to do green. But it could be blue or red. So it could be blue. Um, and then this one here, I mean, you don't want it to be red, so it could be blue. And this you could do green, and then you do red over here. Why would you do red over here? Just because actually it doesn't matter. It could be green. Because they both have a distance of 2 to red and a distance of 1 to blue. And that's my argue is that D1 plus D2, you can always limit this to 1 plus a 2 or 1 plus a 1. And so if you just look at this example where like you try to place the colors as optimal as possible and you just think through each step, then if you were just to come back in here and just count like what's the distance? Well, what's the distance here from red to blue into green? It's 3. What's the distance for this one? Well, this one it has red and green adjacent, right? So you quickly come to an observation. If the degree of a node is greater than or equal to 2, then that means the score will equal to 2. Why? Because if you have at least 2 adjacent nodes, you can always just place the 2 opposing colors to just be directly adjacent to it, a distance of 1 away. So whatever color this is, blue, you can do green and red. And you can do that with anything, it doesn't matter. So if the degree is greater than that, it's going to be score is equal to 2. So I can already determine that all of these, where the degree is greater, are going to be 2. Now everything that is but if you're a leaf node and you're only adjacent to one node, the score has to be 3 because yes, you have a distance of 1, but you're only adjacent to one node. So that means it must travel at least 2 units of distance to get to one of the colors at best case. So just using that like argument, you can solve it by just calculating the degree. You don't even need adjacency list. Just calculating the degree of each node and then incrementing by 2, but if the degree is 1, adding 1 more because you have to travel that 1 extra distance. And then that will be the answer. Okay. Now populate. Right. Okay, so this one, geometry easy. So this one I actually solved. My main problem was that I was using an unordered map instead of using a frequency array. Apparently using a frequency array that is very large. This is a frequency for my actually like works. But yeah, I guess I'll get into why this I had trouble with this after I read the problem statement. Yeah, so geometry easy. Okay. For this problem, you're guaranteed that all elements of A are pairwise distinct. That it makes it a bit easier. You're given an array A containing n non-negative integers, and you want to count the number of ordered quadruples I, J, K, L such that I, J, K, L is between these two ranges. And the values of IJKL are pairwise distinct and it's supposed to form a rectangle such that the XOR of AIAJ is equal to the XOR of AKAL, but also the XOR of AJ with AK is equal to the XOR of AL and AI. So these XORs of your quadruple are defining the side lengths of the rectangle. What was that? Okay, back to it. Okay, I had to step away for a minute. I don't remember. Please note that all side lengths of the rectangles must be positive. Almost yeah. So okay. So let's just like go through one of the examples like this one, or I don't even need this example, but I'm gonna just do kind of set it up. So you could have something like this: 1, 2, 4, 7, or you could have 1, 2, 3, 4, 5, 6, 7, 8, something like that. They'll have to be distinct. And the observation here really is if you take AI, so you're saying AI XOR with AJ, so you have a tuple I, J, K, L. And so what it says is that this has to be equal to the side length defined by AK XOR with AL. And then you also require that AJ XOR with AK is equal to a I XOR with AL. So there's like something you can do here though, which is that I saw is that if you take this one, you can get to here. That is, if this statement is true, then this statement is true as well. And one other thing here, since everything is distinct, anytime you take two distinct integers and you XOR them, it will always be non-zero. So you don't have to worry about the side length ever being zero. The side length will always be positive integers for every pair. So you don't have to worry about that. So if you mix match these together, or how can you go from this one to get to that one? Well, if you just take, so this one has JK, so you need to XOR AI on both sides. So you're going to XOR AI, and then you need to get K over here. So you're going to XOR by AK. Okay, so you XOR these two, and then on this side, you take these and you XOR the AI and AK. And then what happens is these will cancel and this will cancel. And then it'll be left with basically a J XORed with a K equals a I XORed with a L. Therefore, basically, this shows that you can go from this one and then derive. So if this is true, if this is true, if these are equal, then it's guaranteed that this is equal. And since everything is always non-zero, it's not going to be equal to zero. So it'll be a valid pair. Now the other thing to look at here is this is let's say the index of the quadruple I J K L. Let's say it's 1, 2, 3, 4. Right, these are the indices. Um, in this case, you know that that basically these two XORs are equal. So like if A1 XOR with A2 is equal to A3 XOR with A4, it guarantees, like we did above, that the XOR of A2 and A3 will be equal to A1 and A4. just by doing some arithmetic, you can get to there. Just like with just like the same as above. Hopefully that makes sense. And then, but what you can say with this is you can say like, well, how many ways can I like arrange this? So if I found a pair like this, how many ways can I rearrange and work it? Well, I could put the 1, 2 here, and then I could put the whatever I want to put here. I could put 3, 4, or 4, 3 technically. I could switch this. I could do 2, 1 and put 3, 4, 4, 3 here. Or I could do this completely differently and do 1, 2 here and do 2, 1 here and then do 3, 4, 4, 3 here, 3, 4, 4, 3 here. And so all of these will be valid. So there's a total of 8 ways in which I can rearrange these quadruples, and each one is valid. It satisfies the constraints of the problem. It defines a valid rectangle, and they will all count. So all you have to actually count are these quadruples. And here's how easy it is to count these quadruples. Let's say I have a few pairs of values that XOR to something. Let's say I have a few pairs that XOR to 6. So what's something now that XOR to 6? 1 XOR 7 equals 6. Okay. What's something else that XOR to 6? Just trying to come up with some. I think 2. Uh, mm, I mean, this one's easy. 0 XOR 6. What about 5? What's 5 XOR what would equal to 6? Whatever this is, actually. What is this? So 3. So 3 XOR 5 equals 6. And this equals 6. This equals 6. So there are a few ways to get the XOR to 6. And so what you can do is you find all these pairs, the counts of these XOR pairs, or these pairs of integers and their XOR value. And what you can do is you can pick them whatever. So like I could do 1, 7, and I can match 1, 7 with either of these. So what you can kind of see here is that I could pick the 1, 7, or I could pick. So think about it like this. Actually, let's define these XORs as being specific ways. So say this is one way to do an XOR, and let's say this is X1 way, this is X2 way, this is X3 way. How many ways can I pair these together? I can pair X1 with X2, and I can pair X1 with X3, and I can pair X2 with X3. So there are 3 ways. So what you can see is it's basically combinatorics of how many ways can I pick 2 from here? How many ways can I pick 2 from these pair of integers at XOR? Also, another thing that's guaranteed is since all the elements are distinct as well, that there's never going to be a shared element in here, right? Because if an element XORs with something, there's only one element it can XOR with to be equal to 6. And it can't share an integer, like you can't have 1 XOR 7 and then 1 XOR something else, and they're both equal to 6. That is impossible. Um, so given that, it's just choose 2. So it's just you just have to know the count. So the count is 3, and then do this, and then you get that there's 3 ways. So all you have to do is use this formula, n minus 1 over 2, or basically factorial to combinatorics, or like this. So you just have to do that for each XOR, and that's really the solution to the problem. So as you can see here, I just go through, I keep track of the frequency, or the frequency has to be the size of the max XOR, which happens to be up to 1 to 20, which you can check that pretty easily. And then you have I, you go through each element, and then J, so you go through O(n) squared here and calculate XORs and just calculate the frequency of XORs. And then this trick of just adding them like this is just a trick instead of at the end having to use the formula of the frequency times frequency minus 1 divided by 2, instead of using that formula for how to you pick 2 out of n elements. Um, Instead of using that, you can like sum them up over time. But yeah, but it's the same thing. Like basically the difference is like, the frequency originally is 0, then it's 1, so it's going to add 1 when you have 2. That's going to add 2 when you have 3, and that's going to add 3 when you have 4. Like, um, so that'll work. Okay, so the hard one is where it gets kind of tricky, because now you don't have pairwise distinct elements. So that means that, so before, all the pauses, the side length would have never been 0, but now the side length can sometimes be 0. Um, so two things you have to handle here, that you didn't have to handle on the other one, which is that AI XOR AJ can equal 0 now. That is, you can have a side length as 0, which is impossible. Second thing that happens is you can have duplicate elements. And yeah, those are actually basically two things. So everything else it stays the same. Um, okay. So yeah, so how do you handle duplicate elements? So I came up with this really good example. If you have 1 1, 2 2 2, 4 4 4 4 7 7. So if you look at the pairs in here, the possible values, you have a 1 XOR 2, which is 3, 1 XOR 4, which is 5, 1 can also XOR with 7, 6, and then 2 can XOR with 4, and 2 can XOR with 7, which is 5, and then you can have 4 XOR with 7, which is 3. And you say, how many times can these happen? Well, the 1 XOR with 2 is you have 2 times 3, because there's two ways to pick 1, 3 ways to pick 2. And then you just do the same thing for each of them. So then this one's 8, this one's 4, this one's 8, this one is 6, and this one is 8. And then you can go even furthermore. When this counts the number of XORs, so how many XORs of 3 are there? Well, there's 6 plus 8. There's 14. How many ways are there to get XOR 5? There's 14. How many ways to get 6? There's oh wait, this is 12, wasn't it? Oops. Yeah, there's 16. Okay. So there's that many ways to get those XOR values. But the difference from the problem before was you didn't have duplicates. In this case, you have duplicates. So how can you count this? So for the easiest approach, I think, is to separate the two cases. So the first thing is try to handle when you don't have duplicates. How many ways are there to not have duplicates? Okay. So let's go over one example. Let's say you have 1 XOR with 2, right? That's equal to 3. But you also have that 4 XOR with 7 is equal to 3. Um, So if you look at that, that's all the elements right here. Um, and so before it was easy to count this because you would just say, I have 1, 2, 4, and 7. And it was like, how many ways was there to arrange this, right? Well, first off, you would have had only 2 pairs, and then it would have been pretty easy from there. So the difference here is that you need to count this particular way. That is, here's what it is. So 1 and 2 with 4 and 7 works as a quadruple. This works because the 1 XOR with 2 and the 4 XOR with 7 work. And then because all the elements are distinct, it follows the property above. So the middle terms and the outer terms will work always. Um, because that property was derived for when you have distinct. So we're saying we have distinct, but the difference here is that this one could be this one, or it could be this one. And this two could be this two or this two or this two, right? So really what I drew here might be me picking just this pair of 1 and 2. And that is a valid combination. And then I can pick a combination. I can pick this 4 out of these and that 7. So that's a valid combination. So how many do you have of these? So the way to count it is to somewhat like count the total number of pairs you have, right? Well, the total number of pairs that I can generate are that equals the 3 is I wrote over here is 14. It's 6 plus the 8. So I can actually generate a total of 14 pairs. So we could say 14. So I can say from 14 pick 2. Right? How many ways can I pick 2 from the 14? And say, well, that's the answer, right? Because it's like, okay, well, I picked 2 from here, so that will count like picking. Um, that will count if you pick this 2, right? Um, and then you have like many other ways you can pick. I mean, sorry, the 14 over 2 is how many ways you can pick. So like you could pick a pair over here and a pair here. And just remember, over here there are a total of 6 pairs. Over here there are a total of 8 pairs. So you have 8 pairs you can pick over 6 over here. So by the way, the answer will be 6 times 8. It will be 48. But how do you calculate this? Because there could have even more. This instance has 2, but you could have a third pair of integers that XOR to 6, and a fourth, and a fifth, and so on. But what you can see here is that look at your overcounting. So this is kind of how do you correct for the overcount? All you have to do is consider what is an overcount, right? So an overcount is if you pick that and you pick this. If I pick 2 pairs over here, that would be an overcount. So there are this many ways I can overcount on the left, on the 1 and the 2 pairs, and there's this many ways I can overcount over here. Right, this is the number of ways that I can pick 2 pairs from the left side, and there's some ways I can pick 2 pairs from the right side, and those will collide. As long as you pick 2 pairs from the separate sides, from the 1, 2 side and from the 4, 7 side, you're good. So then that gives you your answer to become the total number of pairs minus 6 over 2 minus 8 over 2, 8 over 2, or pick 2 from 8. And so if you kind of like extrapolate this, it's basically the summation of the total number of pairs, where these are all different pairs, but each of these pairs, the XOR is equal to 6 or something, right? And you're going to pick 2 from all of these, but then you're going to subtract, let's say this is xi, like that, but then you're going to have to subtract the summation of xi pick 2, right? You subtract off each individual one because you can't pick two within that block. Like imagine that they're blocks, maybe. Imagine that they're blocks. And for each block, x1, x2, x3, x4, I have a total that I can pick from all of these, and I can pick two pairs from all of this, right? I can do that, but I need to subtract out how many ways I could end up accidentally picking two pairs from here. So if this is the number of pairs, then subtract out that, subtract out this one, and so on. Maybe this is over explaining it, but in another way, and this is one thing to keep track of here, is that we're not talking about the number of elements, we're talking about the number of pairs that equal that XOR. And this problem is dealing with the distinct elements. You have the duplicates, but you're ultimately forming a a distinct pair. So it's the same thing as before. So the only difference is that you overcount unlike before, and so you have to correct for the overcount. And you can correct for the overcount by basically saying that how many pairs there are that equals XOR 6 of ones and twos, how many pairs there are of fours and sevens, and then whatever other numbers. Those, it can be more than just these two numbers, something else that equals 6. Those two numbers as well, you have to subtract the number of ways that you can have picking two pairs in there. So you have to count the number of pairings there are, which is just one number multiplied by the count of the other number, or count of one number multiplied by the count of the other number. And there's always tuples. And then you just want to count, and you just want to be able to subtract how many ways you can pick two from that. And maybe I'm over explaining this one, but like that's how you deal with them, the duplicate elements, but at the same time you deal with the distincts. But there's another case as well where let's use this example still. Um, there's one more like scenario you have to consider for this one. 1 1 2 2 2 4 4 4 4 7 7. So the other scenario is how many ways you can form duplicate pairs, right? So what I mean is like take the 2 and the 4s, right? You could take a 2 and a 2 and a 4 and a 4, right? But this right here, this is not valid. This is not a valid pair. Why? Because 2x or 2 is equal to 0, and you're not allowed to have 0 for a side length. So that's an invalid one. But if you rearrange this, you can make it valid. So if you do this, this is valid. And so the property earlier, where it was like if AI XOR AJ is equal to AK XOR AL. So this property, when these were all distinct, it implied that AJ XOR AK equals AI XOR AL, and that everything is not zero. But in this case, it's different because if you have duplicates, that means you're going to have x XOR with y equals x XOR with y, right? That's kind of like the duplicates. And so that now the rule changes, because now imagine if you're multiplying, because over here in order to go from this side to that side, you did a particular thing where you had to XOR this one. This side you need to XOR by AI, and you need to XOR by AK. So in this case, you have to XOR by this one and XOR by this one. Wait, hold on. That doesn't make sense. Hold on. I think I got a little mixed up. Well, no, because this one works, I think. Yeah. So this one actually works. So if you take this one and XOR both sides by that, well, that's just 0, right? So XOR like that, that's not going to do anything. So so that one's fine. Like these will just cancel. So it's the same thing. But you can see it up here as well, because you can also draw the lines that connect. You can say you connect these two, but then you also connect these two, and like, well, obviously those are the same thing. But what's not going to work out is you can't like rearrange these and have them however you want them. Like you can't do 2, 4, 4, 2, for instance. So that's not going to work because now this is a pattern of x, y, y, x. And so if you take x, y equals y, x, but now if I take the two elements here and here, these two, and I XOR them on both sides. So if I did x XOR y, x XOR y, um, what do you get? Well, you get 0. And that's the problem, right? Now you're getting a 0 side length. So like, so while these are non-zero, but these are is equal to 0, because these are basically this. So you have to be wary of that. So you really can, when you're dealing with duplicates, you really have two scenarios. You have the scenario of you have a distinct element here, and then you have this one, and then you have that one. You can have this, or you could have this. And those are only two possibilities. So so there aren't that many ways. So if you look at the 2, 4, 2, 4 one, you can see how I can kind of do that. And then also I can do that. And you're really limited in what you can do because you can't swap these two. You can this is really all you can do. Um, so the counting is a bit different. Um, so how would you count these? Like if you just did the twos and the fours, how many ways would you say there are to combine, or start with something even easier? Start with one and these. How many ways are there to form like 1, 1, 2, 2 using these two elements? So basically forming 1, 2, and 1, 2, and so on. How many ways are there to do that? Well, how many valid ways are there? So, okay, this one's valid. This one's invalid. This one's invalid. And this one's valid. So you have those two valid ones. Um, but furthermore, look at like how many ways you can do this. Well, how many pairs can you form here with the one? You can form one pair right here. So there's only one pair you can form here. How many pairs can you form here? Well, you can form 3 pairs here. So there's 3 pairs you can form here. So if that's the case, then over here, if you look at this 1 and this 2, right? You can say that um, that if this one is like particular element, so over here I drew like the elements, but let's draw like the index value. So let's say this is you're pairing up 1, 2, and then 3, 4. Okay. So think about it. Over here you can have the 1, 2, and you have 3, 4, and then you can kind of switch it around, and you can say I can do 2, 1, 4, 3. You can also do 3, 4, 1, 2, and you can also do 4, 3, 2, 1. So in total, it's 4 ways that I can arrange this, I think. That would be valid. Yep. So there's 4 ways, but since some of these elements are the same, this is like your x, and this is like, and it's like your x, and it's like your x, and it's like your y. But these x's, so like in this case, I'm pairing 1 with 2, but these x's are exchangeable. That is, I could pair the 3 with a 2, and then do this 4 more times. And when I pair the 3 with the 2, that ends up pairing the 2 with the 4, right? These x's are exchangeable and these y's are exchangeable. So ultimately, you end up with that there are 8 ways still. So there's still 8 ways for something like this when you have two duplicates. And do you have to deal with more duplicates? Like here I'm dealing with like saying 1x or 2, 1x or 2 are equal, right? Well, you can't deal with 3 duplicates because like what the heck is 3 duplicates? Is this? Now you have 3 ones. Well, that's not gonna work. So it has to be like this. And so if you look here, again, it's like how many ways can I pair up the ones with these twos, right? I can label these as 0, 1 and label these as 2, 3, 4. Well, I have 3 ways of doing it. One way of doing this, so I'm always going to pick this 0, 1. Over here, I might pair it with these two, or I might pair it with those two, or I might pair it up with these two. So I have 3 options. So if you do 1 times 3, you get 3. Um, and so what you can say is that um, okay. Okay, I don't know. Okay, so what you can say is this. You can say that how many ways can I pick a pair and pick 2 ones here? There's one way. How many ways can I pick a pair here? And there's 3 ways. How many ways can I pick a pair of 2 fours here? Well, there's 6 ways. Okay, so let's ask a question. If I'm dealing with this particular number, this particular distinct number, and there's 2 instances of it, how many ways can I pair up duplicates? Well, I can. I only have one pair here, so I can pair up the 7, 7. I can pair them up with the duplicates of the 4. There are 6 ways to do that. The duplicates with the 2. That is basically I can pair up with the 2s. I can pair up with the 4s, which really looks like 2x or 7 equals 2x or 7, of course. And then I can pair up with the 1s. And this is the total number of ways. So multiply that by 1. That will give me the total number of like these duplicate combinations, these duplicate quadruplets that I can form. Well, then you have to multiply by a at the end, of course. But um, and that's for the 7 itself. So all you have to do is keep this prefix sum of the number of ways as you iterate through. So like for instance, you'd update the prefix sum for the next one, 1 plus 3 plus 6 plus the one way to be able to pick 7 for whatever comes out here if you have 8s or something. So you just keep updating this prefix sum of basically the number of ways of picking 2 elements of a single value. So pick 2 duplicate elements, um, and you just have to prefix sum that, and then you compute for each step, and you add that sum to the total answer of the number of these duplicate pairs you have. So if we look at the code here, you can see, again, we do the max XOR max in. So here I have 2 frequency arrays, one that will keep the frequency or the count of for each particular element, and then this will keep the frequency of the XOR values. So we're going to be using this choose function, which is how many ways are to pick 2 from n elements. Do array resize. I set this frequency, so you update the frequency for this one, and you do this insertion of the vowels just so that you know what all the distinct values are, so you can iterate over the distinct values, and because even though you have duplicates, you're iterating over the distinct values, but you know how many of that value there are in the array. So even this part here, you do this, and you find out how many there are, and then here you do the prefix for the number of ways, and this is the sum, which is the contribution of the duplicate pairs. And so if you go through each duplicate pair, so each time you're going to start here with a sum. So the prefix ways is 0 at the beginning, so it does nothing. But if prefix ways is whatever, that is basically this thing right here, the 1 plus 3 plus 6. It will be some integer, and you multiply how many ways can I pick 2 elements of my current value, like how many are there and how many ways can I pick 2. And you always update this prefix ways for the next iteration. And then in here, you're going through, and this part is mainly intended for doing the computation for the when you don't have the duplicate pairs. Um, and that one just goes through here. So yeah, you calculate the XOR of those two values, I and j, and you see, have I seen it before? Otherwise, added to the XOR values. You're gonna want to know these XOR values. And you update the frequency of the XOR, which is just basically the frequency of the ith element and the frequency of the jth element. The count of them multiplied together gives you a total count. And here you do the subtraction. This subtraction is doing that part where do I still have it written? Yeah, it's just doing this part really. It's just doing it like in the moment when you're going on the fly, when you're going through here. You're just subtracting for each of these. And by taking the frequency of both of these and multiplying them together, that gives you the number of pairs they form. So then you can just subtract that from answer. So then when you go back through here and you have the frequency XOR, it will add on the frequency XOR. So that adds on this part because it takes the sum and then how many ways can you pick two from the sum. So like even in this example here, it's the 14 over 2 and the subtraction would have been the 6 over 2 and the 8 over 2. I don't know if that explains it. And then you have to add that sum back onto the answer that you computed up here for the duplicate pairs. And that's it. That solves this problem. And that's about all I could solve. Um, the other problems, mm, kind of hard. I guess I'm just gonna look at the editorial real quick and record that, but I'm not going to push my luck. So like colorful tree, that's just counting the number of ways. Didn't really get to that one. Yeah, I mean, I was thinking DP. I just I did not have any idea how to set it up. But, So they use the color of the parent and the color of the current node in their dynamic programming state. Fulfilled if the current coloring already gives menopausal. So that will happen whenever you have at least two children. If you have one children, then to be fulfilled, I'll have to look at the parent, I think. Oh, I don't know. Wow. Yeah, this one would take a while, but I think I upsolved one problem that was hard enough. But this one would be hard to upsolve even. So yeah, I think I'll just keep it with those problems. But yeah, I mean, it was DP and it um, was like that. So it's an interesting one, but I think I'm gonna skip it for this contest. Dynamic programming on a tree. Yeah. So I don't know, like the way to figure this out really is to kind of like determine how you're gonna do dynamic programming on a tree, determine like how you're gonna count. Like it's very much counting's involved, and like determining the transitions. Those are probably the steps to solving it. And like one thing is this is kind of like different than a reroute of the tree. You're not really using a rerouting of the tree. I don't think so. You're just kind of doing these transitions here. Oh, this is a post-order traversal though. Hmm. Okay. Yeah. Okay.